for this video, we'll be talking about the equilibrium constant and a new term, reaction quotient. At the end of this video, these are your objective. You should be able to interpret where the reaction will proceed based on the reaction quotient and equilibrium constant. So you'll be comparing the two. And then you also need to solve problems relating to the equilibrium constant. Let's first define reaction quotient. So reaction quotient is very similar to equilibrium constant. So it's still the ratio of the product and the reactant concentrations or partial pressures. However, the reaction quotient is a general is for general conditions, meaning it doesn't have to be at equilibrium. So the condition could be at any given point during the reaction. Could be the initial point after a stress is introduced or during equilibrium, which we don't know yet. So to be able to write the expression for the reaction quotient, the rules are the same to the equilibrium constant, which we have discussed beforehand, except that the values we're going to input are for non-equilibrium conditions. So you still have two types of reaction quotient. You have the QC and you have the Q. But still, these expressions are in terms of molarity and in terms of atmosphere. Okay, so why do we need to compare the reaction quotient and the equilibrium constant? Well, when we are given a condition which we don't know yet, once we calculate for the reaction quotient, we can determine whether that particular conditions, the given concentrations or partial pressures, is for is already in equilibrium, or whether the reaction would still have to adjust for it to establish equilibrium. Given a given set of conditions in the reaction quotient and determined that Q is equal to K, then we could say that the reaction is already equilibrium. And the system will maintain these conditions since it's already in equilibrium. However, if upon calculating we get a reaction quotient which is less than K, that means our system is not yet at equilibrium, and for it to reach that point, it must proceed forward or form more products. On the other hand, if our reaction quotient is greater than K, then the reaction should proceed backward since it's still not in equilibrium as well, and it has to form more reactants for each to reach equilibrium. So remember that when you have a reversible reaction, the system will always find a way to establish equilibrium. You just need to determine whether it's already at equilibrium. Is it not yet at equilibrium? Okay, for this leftmost and rightmost conditions, and in which direction will it go forward? Will it form more products to reach that equilibrium point, or will it form more reactants? To illustrate the point, let's solve a problem. Okay, so we have this problem. At 1000 Kelvin, the value of the Kp for this reaction, okay, the composition of sulfur trioxide is 0.338. Now we are to predict the direction in which the reaction will proceed toward equilibrium if we are given the initial partial pressures. So we have these values, 0.16, 0.41, and 2.5 atmosphere for sulfur trioxide, sulfur dioxide, and oxygen respectively. Okay. So since these values are said to be initial partial pressures, in no way does the problem tell us that these values are for equilibrium mixtures, then it's safe to use Q. Okay, and then we set up the expression. Remember, product over reactant, and each term are to be raised or is to be raised with its respective coefficient. Okay, We have that. And then we substitute the values and we press equal sign. So we'll get QP of equal to 16. Now, compare this value with the given KP value, which is 0.33. So QP is greater than KP. Okay, and with us, we can conclude that given these initial partial pressures, the system should proceed backward. Okay, since the Q exceeded K, the reaction should proceed backward for E to reach equilibrium. In other words, after we have these initial partial pressures, the system will find a way to produce more reactant and get rid of the excess products so that it can reach equilibrium. Okay. Next, okay, for second sample problem, we have this. Okay, we have calculating the equilibrium concentration given this problem. So for the Haber process, formation of ammonia out of nitrogen and hydrogen, the Kp value is 1.45 times 10 to the negative 5 at 500 degrees Celsius. The partial pressure are 0.928 and 0.432 atmospheres for H2 and N2 respectively. And we are to calculate for the partial pressure of ammonia in this equilibrium mixture. So for this problem, we are given the Kp, we're given partial pressures of hydrogen and nitrogen, and it said here that this is the equilibrium mixture. So meaning all of these values are at equilibrium. We are asked to find the partial pressure of one component at equilibrium. So for this, we'll be using Kp directly. Okay, we have this, and then we try to, since we're looking for the partial pressure of NH3, we're going to rearrange the problem to come up with this equation. Okay. And then we have no problem here since all of these three terms are given already, and you just have to substitute the values. With that, we can calculate for the partial pressure of ammonia, which would give you 0.00224 atmosphere. Okay. You can also try to rationalize since Kp is very, very small. It's way back less than 1. Then you can already deduce that if these are the equilibrium concentrations for the reactant, okay, Kp is very small, meaning we should anticipate that we'll have less product, okay? And based on our calculations, that's true. Our product partial pressure is very, very small compared to the reactant partial pressures. Next, okay? So, you have this next problem, which is about calculating equilibrium concentration from initial concentration. Okay, so let's read the problem together. Okay, a 1 liter flask is filled with 1 mole H2 and 2 moles I2 at 448 degrees Celsius. And the value for the equilibrium constant Kc of this reaction is 50.5. Now, what are the equilibrium concentrations of H2, I2, and HI in molarity? Okay, so we have to understand the problem. Okay, so it says in the problem that a flask is filled with the following moles of gases. And then we are asked about the equilibrium concentrations. So what we're given here are the initial amounts. Okay, the system is not yet at equilibrium with these values. So you're given the initial amount. And then you're tasked to find what the amount would be once the system reaches equilibrium. Okay, So since this is in Kc, we need to use terms in molar concentration. So that's why, okay, so that's why we have to divide the mole with the volume for us to find the molar concentrations. So you get 1 molar H2 or hydrogen gas and 2 molar iodine gas. Now, this problem would introduce us to an ice table. Now, what is an ice table? An ice table is simply a table, and ice means I, initial concentration, C, change, and E, equilibrium. Okay, so this problem is a blend of your mathematics and your chemistry lesson. We're dealing with a chemistry concept, but we'll be using math to solve this one. So you have initial concentration, which we have already solved for. So you have 1 and 2 molars for the reactant. And since there's no mention of any product being put in the flask, we could just assume that there's no product yet. Next, how about change in concentration? Okay, so the change in concentration, we don't know how much less or how much more the initial concentrations would change for it to achieve equilibrium, right? Okay. So we just set an arbitrary variable, just like when you do your work problem or when you had word problems in age, work during your grade 8 lesson. So we'll just assign, okay, so let's assume that our reactants will get or will lose certain number of molar or moles, and we'll just assign that as negative x. So negative x is the unknown amount of H2, which will be converted later into the product. Okay. Now, why is there a negative sign? Because H2 is a reactant, and we assume that reactants will be consumed in the reaction. Okay, negative x. And then also, we're using just negative x because H2 has a coefficient of 1. So that's negative 1 or simply negative. We do the same for I2. Okay, so we also use negative since it's a reactant. And you have x since its coefficient is 1. For the product will be formed, right? So we'll use positive sign. And then since you have a coefficient of 2 here, we'll also use this coefficient 2 here. So this is set using mathematics and also using our knowledge of stoichiometry. Whatever is lost here and formed in the product are stoichiometrically equal. So you have these. Next, for the equilibrium concentrations. For the equilibrium concentrations, we just need to add together the initial and the change. So you have 1 minus x, 2 minus x, and positive 2x, respectively. Okay. Once we have that, okay, let's remove the given to free up space. We try to establish or write the equilibrium constant expression, which is this one. Okay, because we're looking for the equilibrium concentrations, right? Now, we substitute, okay, we know what the equilibrium concentration is. We don't know the equilibrium concentrations yet. However, we have set up the variables we're going to use as substitute for this values. We have 2x quantity squared over 1 minus x times 2 minus x. So I just dropped the zeros to make it less cumbersome to write. But, you know, the significant figures would still do at the end. I'm just dropping it at this point. Anyway, I have established it here to start. Now, we have this, and we try to simplify this. So if we transpose the variables in the denominator to this side, we'll get this. Okay, and then simplifying further to remove any parentheses, we'll get this quadratic equation. Okay, now, of course, at this point, you should be able to get that we're trying to solve for the value of x. Okay, and since this is not a you can say this is not a quadratic equation that is easy to factor out, then you should use the quadratic formula. Okay, negative b plus minus square root of b squared minus 4ac all over 2a. Okay, so that's your math working there. Once you use the quadratic formula, okay, with this standard form of the equation, you'll get two values of x. Since this is a second degree polynomial, okay, you'll get x1 2.323 and x2 0.935. Okay, I hope at this point you can follow, but you can pause the video if you'd like and try to digest. So for yourself, whether you also get this quadratic equation. So note that we solved for x, but what we're looking really for is to find the equilibrium concentrations. What is 1 minus x? What is 2 minus x? What is 2x? So we're a step closer there since we already found two values of x. However, since we're dealing with a real scenario here or real life scenario here, you have to determine whether these two x's would make sense in our scenario. Okay, we try to substitute x1 to 1 minus x, you'll get a negative value. And we're not dealing with a negative concentration. Negative concentration simply wouldn't make sense in the real world. So with that, we reject x1 and we retain x2. Since if we use this to substitute here, here, and here, we won't get any negative concentration. Okay, so we retain this value and then we try to substitute. So H2 concentration is 1 minus x, which would give you 0.065 molar. Iodine gas 2 minus x is equal to 1.065. And hydrogen iodide gas 2x would give you 1.57. Okay, at equilibrium, the concentrations of H2, I2, and HI would have these values.